Hi, my name is Julie Boyle, and I'm the project manager for the courtois.neuromod project. And today, along with Basile Pinsard and Valentina Borghesani, we're going to talk to you about the CNeuromod 2020 data release. In particular, today we're going to talk about availability of the data, quality of data, and some activations. This is part one of a two-part talk, and I'll tell you about part two in a second. So on the menu today, I'm going to start off by giving you some details on the release and some overview of the data. Then Basile is going to take over and give you a description of the pre-processing and quality assessment. And finally, Valentina is going to wrap it all up with some activation maps. I mentioned that this is part one of a two-part talk. Next week, same time, same place is part two. So that's March 30th at 3 p.m. where Elizabeth Dupré will talk about inter-subject correlations related to the data release, and François Pogam will talk about seed-based functional connectivity related to the database. One small point before we delve into the CNeuromod data is that in case you've missed any CNeuromod talks during the previous month, or you want to catch up on one, check out our YouTube channel. The link should be somewhere above my head here, where you can catch up on previous talks, sorry. So CNeuromod 2020 release candidate is pretty much ready to go, as you'll see from our side. The question that begs, and I think if you've heard me talk before, you're going to be asking this question, and it's certainly a question that weighs heavily on us as a team, is when. For those of you who heard me talk during the platform talk last week, you would have heard that we ran into some resistance with the local authorities, in particular our ethics committee, on the idea of openly sharing the data. There's definitely been some disagreement on interpretations of provincial and Canadian law regarding open data sharing. But the good news is we found a path forward. The door has creaked open a bit, and we can find our way forward, and we're really hoping to have the data ready very soon. Part of that path forward definitely involved us having to hire some external lawyers with some expertise in data sharing, who helped us work on some data transfer agreements and just all the documents related to the data release. So we're hoping to finalize the documents by late spring, so stay tuned. Definitely as soon as we have these documents ready, we will be releasing the data. So I promise the data is coming. So the next question is how? So you can get access to the data through a process called registered access. Any PI with university credentials will have the right to access the data. That PI will just need to go onto our website and write a little blurb about the type of research they want to do. The reason we ask for that blurb is really to make sure that it merges with, or at least congruent with, the type of consent that we received from participants. And then both our institution and the PI's institution will sign a data transfer agreement, and voila, you have the data. If you want more information, check out the cneuromod.ca link. Should be somewhere to my left. There you're going to find really on the front page a link that's called Get Access. It's a green square. And already you can sign up to get the data. And as soon as the data is ready, we'll send you an email. We can start the process of getting all these documents filled out. The data format, I'm not going to tell you too much about the data format because Basile is about to go into tons of details with you guys. But quickly, the data is pre-processed in fMRI Prep LTS. It's formatted in BIDs, and the data is going to be available through DataLad. Now, for those of you that don't know much about DataLad, DataLad allows you to publicly show the structure of a data, so you'll be able to see the contents of the data publicly. But if you go and click on a link and try and download some data, you're going to be stopped unless you've gone through this registered access process, and we've given you a unique identifier and password. So check it out. More information, cneuromod.ca if you want to learn more about the release candidate or sign up to get the data once it's ready to be released. So for most of you, you already know that we have 6 participants, or n is equal to 6. The general inclusion in order to be part of the study were quite broad. As you can imagine, we're not doing group-based analyses with an n of 6. So the inclusion criteria really to just be generally healthy, to be MRI and MEG compatible, that's a little bit obvious in order to be able to be scanned, to have a normal hearing for their age. Participants also need to have a solid comprehension of the English language. As you're going to hear about in a second, all the stimuli that we present are presented in English so far, so people have to be able to understand what's going on in films and movies. And most importantly is point 5, which is they need to be willing to be intensively scanned for at least 5 years. And of course, we're really grateful for all 6 participants who signed up. You can see on the table here subjects 1 through 6 and a little bit of information about them. And on the sex column, you'll see that we have 3 women and 3 men. At the age of recruitment, our participants range in age from 31 to 47. All participants are right-handed, and 3 of our participants are native francophones, 2 are native anglophones, and 1 is bilingual. In terms of acquisitions, we acquired data, or at least fMRI data, on the Siemens 3T Prisma Fit scanner that's located here at UNF in our basement, more or less at the hospital's entrance next door. And we use a 64-channel head and neck coil. In terms of functional sequence, we acquire 3 hours per week per subject of functional data. The sequence that we use was as a CMRR sequence that was developed for the Human Connectome project. The sequence has been adapted a little bit and tweaked for our purpose, and it's an accelerated simultaneous multi-slice gradient ecoplanar sequence. Our slice acceleration factor is 4. Our TR is 1.49 seconds. Our TE is 37 milliseconds. Our flip angle is 52 degrees. Our voxel size is 2 millimeters by 2 millimeters by 2 millimeters. We have 60 slices per volume, and our acquisition matrix is 96 by 96. We also acquire anatomical sequences about 4 times per year. We acquire both brain and cervical sequences. I haven't put the details of the anatomical sequences because they won't be talked about really in this talk. But if you want more details, check out docs.neuromod.ca. And if you go to MRI, you're going to find all the details related to the anatomical sequences as well as the functional sequences. So lastly, I'm going to talk to you about the types of data sets that are included in the cNeuromod release. First, there's movie 10, which is about 10 hours and 16 minutes of watching movies. Participants watched The Wolf of Wall Street, Born Supremacy, Life and Hidden Figures. And Life and Hidden Figures have an asterisk because they were watched twice. They also watched season 1 and season 2 of Friends. That's about 18 hours and 57 minutes of data. We're also including 2 anatomical sessions that include both brain and cervical data. And lastly, that data set's going to include HCP-TRT, which stands for HCP, the Human Connectome Project Test Retest. And that's about 8 hours and 25 minutes of functional data. Valentina's, after Basile, is going to tell you all about HCP-TRT, so I won't go into details, but I'll give you just another general overview to prepare you for that talk. So each of our participants did 14 to 15 repetitions of the 7 HCP tasks, as well as 5 resting states. Each one of the tasks, the HCP tasks at least span multiple cognitive functions, including language and social cognitions, for example, as well as stimulus modality. They have auditory studies, stories, and visual prompts. And the order of fMRI tasks was randomized, and the order of the resting state fMRI was counterbalanced, odd versus even sessions. And I'm going to leave you, but Basile is about to give you, to talk to you about quality control and pre-processing. And if you have any more questions, I'll see you at the live Q&A session in a bit. Bye.
Hi, it's Basile again. I'm the data manager for the courtois.neuromod project, and I will talk a bit about data management. For the dataset distribution, we rely on the community standard bit specification. This specification describes how to structure neuroimaging files in a standard way to allow direct input to preprocessing pipelines. The bit is stored in a DataLad dataset. DataLad is an overlay of a Git, a distributed versioning tool, and Git Annex, an extension of Git for large file management. This tool allows to track file changes, manage release preparation and maintenance in a collaborative setting. It also provides full provenance by linking modular separate datasets, which means one dataset uses as input another dataset by storing its exact version as a Git commit. As you can see on this figure, you can have a hierarchy of nested and linked dataset. It also includes a reproducibility tool that saves the code execution performance dataset and the changes it created, which allows to have a fully reproducible analysis pipeline. And the code execution is better to be stored in containers to have also a reproducible execution environment. So you've seen the other day all the type of data we acquire in the project, but acquisition is just the beginning of the journey for the data. For each type of data acquired, we are developing workflows to convert and measure data in the bid specification. So you can see here the MRI data, the stimuli and eye tracking data, which we are starting to collect, and the biopack physiological data that we acquired now for a while. So our bids is a bit particular because we acquired not one, but numerous datasets to keep things modular. We have a top dataset, neuromod, which contains different bid sub-datasets for each of the facets of the project. So the anatomical, the HCP-TRT, movie 10, Friends, Shinobi, etc. And all the datasets are stored in a file-based manner. So what you see here are folders and files. And each of the folder here in bold is in fact a dataset to keep things modular. We're in the process of moving to a new approach called YODA, which focuses on tracking provenance of data and reproducibility of all transformation applied to data. Part of this approach diverges from the standard bids, such as that the derivatives are no longer stored as a child folder of the raw dataset. In that process, we will track which version of the raw data is used to create the bids, and each of these sources to each sub-dataset is referenced in source data. So the ICOM, the physio, or the eye tracking data that you can see here are in fact linking to the raw data which are not converted to bids yet. So the MRI data are converted from the ICOMs to bids with UDConv, and we are extracting as much metadata as possible and generate the base structure of the sub-dataset. The non-anonymized data are labeled as sensitive and are then defaced. So we erase a portion of the face which have identifiable features. And that allows keep the non-defaced volume in history, but they are not accessible to the user. So we developed the task in PsychoPy and output event files in the bid standard in terms of file structure and naming, as well as file content, as much as possible. So this way, this requires minimal post-processing before being merged in the bid. For task-specific files, for example, the video games, we will ship emulator recordings, so the Gym Retro BK2 files. But we also gonna extract offline a set of variables of interest like the button presses or the game events, or the game variables like life or ammunition. For the physiological data, this requires more work as we have no control over the proprietary acknowledged software. We will use Fizz2Bids to crop session-long recording to run recording in a bids-like structure. These files will also require most post-processing before including them in the dataset and being able to be used by the users. The signals are highly corrupted by the scanner gradients, and of course, we will need to quality check after they are corrected. François Lespinasse will present more on that topic in a dedicated talk. As you can see here, with the YODA approach, we reference the version of raw DICOM physiological data and eye tracking as sources, but these will not be shared because they are sensitive and they have like identifiable features for the participant. So once these files are converted and merged in the bids tree that we can see here, we moved on to producing derivatives. We do so by using pipelines, which are containerized for reproducibility. The container has themselves referenced in the derivative subdataset in which they've been used, but I omit it in the figure for simplicity. So the neuromod preprocess will be a separate super dataset that references the bid dataset in many places. Some of the pipelines are only applied to the anatomical subdataset, such as SMRI prep here, or track to flow, which is like a diffusion MRI pipeline. And some will only reference the functional one, like fMRI prep. SMRI prep runs internally FreeSurfer, which we reference at the root for users who want to use it, and want only to use fMRI prep, FreeSurfer, I mean. Then we could think of future shared analysis, for example, running GLMs on, let's say, HCP-TRT, and in that case, the HCP-TRT GLMs will reference fMRI prep output as its source data. So in the raw bids, the raw bids was some kind of tree architecture, but the preprocessed dataset is some kind of weird complex graph which is self-referencing itself, and is connected to the raw bits at different places. When a user of the dataset wants to run analysis, she or he installs the top CNeuromod preprocess because he likely wants to have the preprocessed data rather than the raw, and he references it in his project and gets only the same dataset that she or needs. She or might want to combine fractal-free outputs with DIPAC embeddings on movie 10 only, for example. Now I will present you some preliminary QC metrics on the dataset. One issue that we particularly try to reduce is motion. We have custom head case to maintain the head in a fixed position. And here is the distribution of the mean per run of frame-wise displacement, a measure that converts rotation to distance and averages with translation. We can see that despite the head cases, there are important differences between the participants, the subject 3 and subject 4 showing extremely limited motion. If we now look at the max FD value per run, we can see that similar trends between participants, but you can also see that P03, who has lower motion than P04 on average, has a few larger motion excursions than P04. So subject difference could be partly attributed to the head case milling variability, and like a tighter head case leading to better motion level. We can also try to look at the task effect of movement. So here's a distribution of mean FD per task in HCP-TRT. You can see that, as expected, the motor tasks show higher motions than the rest of the task, but the resting state shows even higher motion than the motor task. There could be an effect of the duration of the run, as the resting state is 15 minutes long, and maybe the engagement, as Tammy van der Waal showed when comparing video and passive rest. Here, if we compare with movie 10 data, which runs about 10 minutes long, we can see higher motions than in most HCP-TRT tasks, but still lower motion than resting state. Now we also measure the temporal signal to noise ratio, which is a metric of signal stability. The higher the noise, the lower the quality. We can see that the subject difference are similar to the motion metrics, with the lower mover having higher TSNR. In summary, thanks to the setup and the participant dedication, the preliminary QC measures are up to or above standard. We will continue to iterate on the setup to further improve the quality when problematic, and motion does not only impact the fMRI data, but also the eye tracker, which is super sensitive to the drift of the participant position. So now I will let Valentina present the GNM analysis of the HCP-TRT task. Thank you.
Hi, I'm Valentina, and I'm here to show you some brain maps. Because how could a brain data presentation not include some brains with colored blobs? So Julie showed you what data we acquired and how you can get access to it. And then Basile showed you how is it organized and how unique it is, not only in its size, but also in its quality. Now it's my turn to show you what we did with the activation maps that we acquire within the ACP test-retest protocol. So first of all, task by task, subject by subject, and session by session, we analyze the behavioral performance, reaction times, and accuracy as appropriate, to ensure compliance with the tasks as well as flag eventual oddities. Then we performed basic mass univariate analysis of the main contrast of interest. As a reminder, the 7 ACP tasks span over multiple cognitive functions, from language to social cognition, and require processing of stimuli of different modalities. We have auditory stories, visual prompts. So overall, at least 18 cognitively and neurally meaningful contrasts can be performed, comparing pairs of task conditions or a given condition versus the implicit baseline. So the unique characteristic of CNeuromod dataset is that we have collected multiple repetitions of the full protocol, which means that it will be possible to investigate variation not only across subjects and tasks, but also sessions. So let's take it one task at a time and compare our maps to those of the original paper from the ACP task force. So the first task is the language task. And here, subjects are asked to listen to a story or a math problem and probed with a comprehension question at the end. As you can see on the left, the behavioral performance, both in terms of accuracy and reaction times, is pretty constant across all the sessions for all the subjects, and accuracy is very high. Consider that this is an adaptive task, so it becomes harder and harder the better the participants are at performing it. Then we can see how the brain maps look like. And here we have on the first row an example of just for one subject, one session. And then in the bottom row, we see the fixed effect model across all the 14 sessions that we acquire in these subjects. And I will always be showing you maps of subject number 1, just because it's just an example. But then, of course, we can also look at the average group map resulting from the contrast story versus math. And the results, as you can appreciate, are reproducing nicely the original functional results from Bark and colleague. And we see this nice, fairly left lateralized activation along the temporal regions, in particular anterior temporal and superior temporal. The social cognition tasks require subjects to view clips of objects that are moving on the screen, either completely randomly or in a way that suggests a social interaction. So here, in terms of accuracy, well, there is a ground truth, but the subjects are also given the chance to respond that they are not sure whether to classify that trial as social or random. So we see that accuracy, it's very variable. I would say fairly low, but that's mostly because subjects do rely a lot on the option to reply not sure. Reaction times, again, are pretty constant across all the sessions for all the subjects. Again, we can see how the individual brain maps look for one session or for the 14 sessions of, again, subject number 1, and the group average. Again, the results are nicely replicating the occipital ventral stream visual processing that we would expect given this task. Perhaps we see less of the frontal activation compared to the original result, but I do want to see these plots in volumetric space using the same cut as the previous study, because I think this might be a bit of a thresholding and visualization issue. In the motor task, subjects move their right hand, right foot, left foot, or tongue. And here, look how beautiful the homunculus along the motor cortex is just in one subject, one session. You really don't need much more. And then, of course, the average map would nicely match previous results and clearly draw the motor cortex across all subjects. As far as the relational processing task goes, participants are seeing either 2 pairs of objects or 1 object and 2 foils, and they have to judge whether they share the same shape or texture. Performance, again, is variable across subjects, but overall very good in all of them. And again, reaction times are mostly constant across the sessions. And the individual maps, as well as the average across all participants, show exactly what we would expect, which is this heightened activity in the occipital lobe for the visual processing of the objects to compare their shape and texture. Again, we might think that they're a bit missing something frontal compared to the original study, but as I said, we will have a look at the volumetric images. In the emotion task, participants judged again the similarity of visually presented stimuli, in this case either faces or shapes. And what is critical here is that the faces have emotionally charged expression, so either angry or fearful. Behavioral performance is basically at ceiling for all the subjects, and reaction times are fast and constant across all sessions. The single subject results, both within a session and across the 14 sessions, as well as the group average, nicely highlight the ventral visual stream, very focused in processing these faces and shapes. And again, I apologize, but in this not great cut that I chose, you cannot really appreciate subcortical structure, so that will require another visualization to check the amygdala and insula of our subjects. In the gambling task, participants are asked to guess whether the next number that they will see is higher or lower than 5. And if they are correct, they get a reward, hypothetical money win. And if they're not correct, they lose, they get a punishment. So here, there's not really accuracy to speak of in terms of a ground truth, whether they're correct or not, but we can look at their reaction times and see that they possibly tend to get a little bit faster. Subjects might realize that is a block design and start replying, always with the same response. The brain maps, again, both at the single subject level and at the group level, are exactly what we would expect, pending focusing on those subcortical structures that in this case are really critical. We have reached the last task, which is a working memory task. So here participants perform either a 0-back or 2-back memory task. So we can look at their brain map. In their accuracy is very high and reaction times are, again, possibly getting a bit faster across sessions. But what is interesting are the brain maps by memory load. So here we see that the 2-back task, which requires more attention and more effort, lights up the frontoparietal network linked with attention much more than the 0-back task. And what is interesting is that the subjects perform this task across different semantic category, which means that we can also look, and here I'm showing you again the results for just one subject, but you can imagine the group average. So we can look at these results by stimulus category. So we see face area, places areas, tools and body parts place area along the ventral visual stream. And the results, both at the individual subject level and at the group level, are as expected, as we would expect. But I should also highlight that this is not a proper visual localizer, so we will add proper visual localizers in the future releases of the data. So as I mentioned, we have this multiple repetition, which means that we can investigate similarities in brain activation across subject, tasks, and session. So here you can see the 6 subjects that nicely cluster, but with clear effects of session and task condition within each cluster. Averaging across sessions, we can better appreciate the subject and condition effects that are hiding in the bigger matrix. And in the end, averaging across subjects, we replicate the task clustering that we observed in previous similar work from the individual brain charting group, for example. So hopefully we'll soon be flooded with your requests to access the data, and we really look forward to seeing all the great science that will stem from it. Let me just end with a couple of reminders. So next week, we will have a second talk on the data release, focusing on inter-subject correlation and seed-based functional connectivity. And you can find us online in various platforms, depending on your goals and needs. And finally, I would really like to thank all the people behind courtois.neuromod, in particular the subjects and the scanning team, because it's only thanks to their commitment and hard work that this data collection and release has been possible in the midst of all that's happening in the world right now. We also acknowledge the incredible generosity of our sponsor, chiefly the Fondation Courtois, and all of our partners, institutions, and university. And now the floor is open for your questions and comments.